Okay, so welcome everybody to the SFU Sports Analytics Virtual Seminar Series. We're on episode 27. Today we have Tyrel Stokes and Brendan Kumagai, who will speak to us today about Bayesian space-time models for possession added value in hockey. So Tyrel Stokes is a PhD candidate in statistics at McGill University and a part-time data scientist working at Zealous Analytics, working currently on problems in basketball. His academic research is split between theory and methods for understanding misspecification and bias in causal inference, and more applied work focusing on causal effects, injury, and prediction in sports. For fun, Tyrel likes to play hockey, boulder, sing, and pretend to understand chess. Brendan Kumagai is a first-year master's student at SFU under the supervision of Dr. Tim Swartz and a hockey data science intern at Stathletes. He completed his bachelor's in math and stats from Master University in 2020, and he's interned as a data analyst with the Canadian Tire Sports Analytics team and the McMaster Visual Neuroscience Lab. His lifelong passion for hockey and statistics led him to pursue sports analytics as a career path, with interest in how Bayesian statistics, spatiotemporal statistics, and machine learning can be used to gain insights into the sport of hockey. Oops, excuse me. Okay, so in terms of their topic today, so they're going to, building off previous work in basketball, soccer, and hockey, they will consider offensive play sequences from event-level hockey data as realizations from stochastic processes. Specifically, they will use INLA to fit Bayesian space-time models, which allow them to simulate from the posterior predictive distribution of possession sequences from any point in the offensive zone and value possession in the offensive zone as play evolves from the rush to prolonged offensive possession. Using the posterior predictive distribution and inspired by expected threat level models, they will build a metric which quantifies the added value of observed actions to the possession sequence. They will then discuss insights from the model on OHL or Ontario Hockey League data and extensions to the full ice data. And with that, I will turn it over to you both, and thank you very much for being here.
Awesome, thanks so much. I'm just gonna share here. Okay, okay, yeah, so thanks for the introduction. We're excited to be here. So yeah, like we said, we're going to be kind of talking about these Bayesian space-time models and sort of a specific way of getting at something like an expected possession value and some of the, I guess, metrics that we can kind of build from that. We're two of us here presenting today, but really this was a group effort of four. A lot of this work comes from work we did for the Big Data Cup last year. And our two other teammates are Thibaut and Mick. Thibaut and Mick are two really excellent data analysts that really understand hockey and how coaches think. In fact, a lot of this work was sort of inspired by some work that Thibaut had done on sort of understanding possessions and stuff like that. And really a lot of the kinds of approaches and questions and what we were trying to answer kind of come from their expertise of understanding what coaches want to understand and sort of using that domain hockey knowledge. So these are just a little bit about them, and I'm going to link to some of their work, which we won't necessarily have time to go into, of how they sort of used some of the outputs from this work to combine with traditional hockey scouting for team and player analysis. So yeah, kind of, I guess, just broadly, just to kind of set the stage, we're going to be talking about expected possession values a lot. The goal of these kinds of models broadly is, like it says, you want to find some sort of expected value of the rest of a possession at some point in space and time. And typically downstream, we want to be able to sort of quantify different player contributions, or at the very least sort of understand the value of different actions in a sport. So just to give you a sense of where we're headed, kind of like we said, so suppose you're in this red box here. We want to be able to kind of quantify how valuable is it being at that spot on the ice, and also how valuable is it to take different actions at that spot on the ice. The blue dot represents in our data a shot. And so the way we're going to kind of figure out how valuable taking a shot in this kind of location is you can see all these gray lines. Those are simulated paths kind of coming from that point. And so we're going to build sort of the kind of necessary machinery to be able to simulate sequences of plays and possession paths that look like the kind of sequences in our data, And then we're going to sort of average the value of those paths to be able to get the sense of how valuable is it being in some spot, or how valuable is it to take like different actions. And that's really kind of the goal. But in the broader expected possession value literature, you don't necessarily need to build a full simulation device to get that. That's sort of like our particular approach, which sort of matched, the data we had, as well as the sports specifics. But in general, an expected possession value thing might look something like this. So we can see here we have the purple dot, which matches up to entering the zone. At that point, the expected possession value, according to our model, is something like 1.3 or something like that. So we expect maybe 1.3 out of 100 possessions from that point to result in a goal. We see there's a pass slightly inside the zone. The possession value goes up slightly. There's a second pass, which seems to change almost nothing at all. And then finally, we get to this kind of shot that's near the crease, and the expected possession value goes up a lot. This is just one way of sort of looking at it, where we looked at the values of those actions, but we could also think about the values of the ice, for example. So this is just kind of more classically what we would think of expected possession value, and on the right is sort of our particular approach. We want to kind of think of expected possession value as sort of a stock ticker, which at every kind of moment that we can, we want to kind of say how valuable the possession is. So a couple of the kind of key things that we were really thinking about here was how can we adapt EPV to hockey? So specifically building on work in soccer and basketball, particularly a paper by Servon et al. In basketball, which was really influential, working on tracking data. How can we adapt that to some of the specific hockey needs? How can we deal with particular constraints in our data, which Brendan's going to talk to us about a little bit later? Given those constraints in our data, how can we kind of get as much insight and information from the models and the quantities that we end up generating? And then we didn't have full tracking data for this, which again, Brendan's going to talk a little bit more, but we wanted to kind of think about how could we set up at least the bones or the structure of this model, such that if we had full tracking data, earpiece fell out, such that if we had access to the full tracking data, that we would be able to scale that like relatively easily. So thinking about that in the future. And we also wanted to think, well, how do we want to value players based on this model? So I'm going to start out, I guess, a little bit backwards. You can really kind of classify expected possession values into two types in terms of how they value players. And the two general approaches is either this kind of models are going to condition directly on players, or instead our models are going to be sort of marginal across all the players. And we're going to think about how valuable players are with respect to the actions they do or some function of the residuals. So the Servon et al. Paper, which we're building off of, mostly in basketball, takes this kind of conditioning approach, whereas a lot of the work in soccer and hockey, which has a similar flavor, took this kind of action and residual method. Even though we're inspired mostly by this basketball paper, we're going to end up taking the second route, where we're not going to condition on the players, largely because we didn't think we were able to with the data that we have. Secondly, we talked a little bit about, we want to think about sport-specific considerations. A really simple kind of low-dimensional summary of how kind of different sports work is you could maybe think of things on a continuum from static to fluid and low to high event. Where fluid or like dynamic, what we mean by that is the sort of structure in the meaningful moments of the game is sort of changing constantly. Thinking of soccer is a really good example. There's lots of little micro passes and micro adjustments of the offense and the defense. Something very static, maybe like baseball, where the important things happen in this kind of discrete state-space way, where before every pitch, we sort of know the exact state of the game, the outs, the ball count, strike count, where the runners on base are, etc. And then low event thinking again about soccer, we're specifically thinking about high information events, which typically are things like goals or scoring outcomes. Soccer typically doesn't have very many. Basketball, on the other hand, tends to have a lot. And kind of in our work, we're kind of thinking about hockey living somewhere in this triangle of soccer and basketball, probably closer to the soccer end, where it's reasonably fluid, although once the kind of play develops, there's kind of sometimes more of a set kind of offensive and defensive structure especially in the offensive zone. But yeah, still relatively dynamic and not that many goals compared to something like basketball.
And now looking at the data that we used for this particular project, we took it from the Stathletes Big Data Cup, which occurred last February. And this included a 40-game sample of extended play-by-play data from the Erie Otters in the 1920 season. And basically, for those of you who don't know much about like the state of public data and hockey analytics, generally, for most big leagues, they have data on shot locations and face-off locations, but not much else beyond that. So this data here provided by Stathletes included some additional insights and some new events that allowed us to fill in the gaps in some places. So now we had passes, including the location of both the passer and the intended target, recoveries, and zone entries. And overall, there were about 70,000 events in this data. But for our project, since we're focusing on the offensive zone at even strength, we were down to about 24,000 events to work with. And another important thing to note is that although we had the location of both the puck and the players involved in the actions, we had no other information about any of the other players on the ice. So that kind of, that was a bit of a tricky thing that we had to work through, which Tyrel will kind of talk a bit more about later. Then looking at a bit of a visual representation of what this data looked like, we have the rink plot there that shows us basically what's going on, and we have kind of this discrete event to event jump as we go. So we have an entry, then we have a couple of passes, a shot, a turnover, and so on. And basically that's kind of the data we have. We have the players and the locations of these events. And we also have some additional details, like for example, on the shot, we know that it's a snapshot on net. And there's a few other things that we have that I didn't list in the table below there, like whether there's traffic or not, or whether there's a one-timer or there's a deflection and so on. And with this data here, there's a few different things like touching on what kind of talking about what Tyrel was touching on earlier. With the models, we don't believe that we can credibly and meaningfully incorporate player effects into the submodels just based off of the fact that we only have about 24,000 observations to work with. So we're going to try to evaluate players through the residuals of the models. And in addition to that, since we don't have tracking data, our data is already discrete, as I mentioned, which frees us from quite a bit of the complexity and computational burden that we see in the Cervone et al. EPV paper. And the last thing, since we're missing the defender and teammate location data, you can kind of treat the offensive and defensive structures as latent states. And we're going to use time since entry as kind of a proxy for this latent state and like how structured the play is, which we'll kind of dive into deeper later on.
Perfect. So yeah, just kind of thinking a little bit about the math and the kind of modeling. This kind of expression is coming from the Cervone et al. Paper, where they think about expected possession variable as being this expectation of some result of the possession in half-court basketball. That's typically 0 points, 2 points, or 3 points, like however the possession ends, given all of the sort of information up to some time. So for us, we're obviously going to have to adapt what the result is. But a couple of kind of insights is, again, kind of really thinking about possessions and their outcomes as being these stochastic processes, which evolve over space and time. That was kind of very useful for the approach that we end up taking. And also they kind of spend a lot of time thinking about sort of stopping times about the possessions. And so if we're going to adapt this to hockey, we really need to kind of define how and when possessions are going to end if we're going to be able to treat these like a stochastic process in a reasonable way. A couple other things, we're kind of coming at this from the opposite end of the Cervone et al. Paper. The Cervone et al. Paper start with this unbelievably complicated tracking data, and the whole kind of point of the paper is how can we take advantage of that without being overwhelmed to estimate these kinds of expectations. Whereas our data is not so big. So we're going to aim for more than just getting expectations. So specifically, we're going to try to get a full distribution to capture sort of uncertainty and noise in this process, just because we're, like we said, we're not as burdened by the computational complexity. The other thing that's a little bit difficult, and this comes to kind of sport-specific adaptations, goals are rare in hockey. So kind of taking the lead from like things like soccer, we're going to think about expected goals as our targeted outcome. So what we're going to try to get is a posterior predictive distribution over the expected goals in these different possession levels. But we really want to maintain the relationship between expected goals and goals, because that's the fundamental currency in a sport like hockey. So just to give it a little bit more model formulation, like I said, we want this kind of posterior predictive distribution where for the expected goals at the end of the possession, where T is this kind of random variable representing the sort of stopping state. That's just an integral over some likelihood for that state with respect to the posterior. And then kind of below, we can kind of see a form that we adapted from Cervone et al. Of thinking about how to get the sort of expected goals at the end of a possession. And the way you get that is sort of this integral over all of the possible sort of paths. So all of the sort of possession paths. And really the bulk of this work is trying to answer the question of how are we going to integrate over the possible possession paths. And the way we're going to do this is form a forward simulation. So we want to get this kind of distribution of paths. We want to simulate that forward. And what we found is that in order to do that, we basically need this one joint distribution, which is the joint distribution of the value in the sort of like next action, the sort of state and action set of where we end up being, as well as the sort of space and time bit. And you could chop this up any way that you wanted, but particularly we found it useful to chop it up this way, where we have the sort of value model conditional on the state and the like sort of space and time location. And then you have the sort of state and action models conditional on where you are in space and time. And finally, these sort of space time models. So in order to do this more in simulation, we start with the space time, we move to the state and action, and then we get the values from that. So essentially, if we're able to propose models for these kind of three broad classes of models that work reasonably well, we should be able to use forward simulation to get a distribution of the possessions. And in fact, we can get more than just the sort of expected goals. We can also get other sort of interesting things from those possessions. So that's what we're going to be targeting, and we're going to kind of talk about some of these different models and how we kind of approached proposing models for them and making them work. So just for kind of illustrative purposes, because I think they're the easiest to understand, and the approach we use for them is relevant to all of the different model types, Brendan's going to start talking about the sort of state and action models.
Yeah, so for these state action models, we kind of treated them as a Markov process. So the transition from action to action and how offensive sequences develop can kind of be represented by this diagram here, which we worked out by slogging through the data and consulting with Mick and Thibault. And basically how it works is that we're going to start off each offensive sequence with a zone entry. Then we're going to cycle through some combination of pass, recovery, shot, or turnover, until we end up in one of the absorbing states in red there, in either a whistle or an exit. And also we have this goal state here in green, which is kind of an absorbing state, like theoretically, if in a real hockey game, obviously a play stops with a goal. But I'm going to pass it over to Tyrel to kind of talk a little bit more about that quick, just because we kind of treat it a bit differently in our model.
Yeah, like Brendan's saying, typically in previous hockey work, people are working with direct kind of discrete markup chains, and often goals is like a nice absorbing state. Here, because we're kind of trying to do these continuous space-time simulations, it's not really practical for us to treat goals in absorbing state. And like we said, we want to kind of target expected goals directly, partly because goals are so rare. We don't want to have to do tens of thousands of simulations for every kind of bit. But we really need to maintain the connection between expected goals and their representation as an expectation of goals, like it says. So what we kind of do is think about goals as a, for some reason it's not letting me, oh, there it is, as a branching state. So every time we get to a shot, the possession accumulates the expected goals of that shot. But we also continue the simulation in the case that it didn't, that we didn't score, but we downweight the rest of that simulation and all of the value that we accumulate with the probability 1 minus the expected goal. So we sort of accumulate the expected goals in our path, plus whatever is downstream, but that gets down weighted by 1 minus the expected goals. So at the bottom, we have like an example formula. Suppose we had K shots in a particular possession. The first shot, we would get the full expected goals, but all of the further ones would end up getting down weighted by the product of 1 minus of the previous value of the goals. And that's going to allow us to keep treating expected goals probabilistically and keep its relationship with goals while not having to run as many simulations.
Now returning back to the Markov process that I showed you guys before, this diagram provides us with a nice way to, like a nice skeleton for how offensive sequences develop. But we want to go beyond that, and we want to kind of show how it flows by getting transition probabilities for this. And we do this by using these action transition models here on the left. And to kind of illustrate how this works, I'm going to focus in on an example where we just look at the transitions from recoveries. So following a recovery in our diagram here, we can move to either a pass, a shot, or a turnover. And let's take a look, just a step-by-step walkthrough of how we're going to get the transition probabilities for these and what's going to be so special about ours versus just the general ones that have been used in the past. So these spatial maps here kind of represent the actual density of, or the observed density of where passes, shots, and turnovers have occurred on the ice, given the actual data after a recovery. Then using that, no problem. Then using that, we're going to take this data in, the spatial data, and we're going to fit a Poisson regression model using INLA. And INLA is a Bayesian approximate Bayesian inference method that allows us to add in a spatial temporal effect by doing the following. So we're basically going to chop up the ice here into a bunch of little triangles just shown by this mesh here. And using this mesh, we're going to like spatially interpolate over all the points inside of, or over all the points within the triangle to get these nice spatial maps as Tyrel showed us there. And these spatial maps match up pretty well with the actual data. And they give us like a nice representation of it. And using these spatial maps here, now that we have them outputted from our Poisson regression model, we can use what's called the Poisson trick to turn these from just singular regression models each into these probability maps on the far right here. And what's so great about these probability maps is that they not only give us transition probabilities from a recovery to whatever event we're going to move to next, but they also vary dynamic spatially. So for example, if you're in front of the net, you're a lot more likely to take a shot, whereas if you're behind the net, you're probably more likely to pass or turn the puck over next. And moving on from there, we actually go beyond that a little bit and we add in another component. Like I mentioned before, we want spatio-temporally dynamic transition probabilities. So we also add in a time component as well. And basically here, we kind of bin the data into groups of like 0 to 2 seconds, 3 to 5, 6 to 10, and 11 plus. And what this allows us to do is kind of approximate the difference between rush state. So like rush play when you're just entering the zone and everyone's rushing up the ice versus established offense when you're deep into the play and everyone's back into the zone and it's a lot more structured. So in the rush state, you're going to see like looser structures, a lot more odd man rushes, and it's going to be a lot easier to get into valuable space and get good chances from there. Whereas later on in the play, when the defensive team's all back in the zone, they're all going to be set up in a formation that the coach kind of specifies. That's going to be specifically designed to mitigate as much offensive chances as you can. And as you can see in the diagram here, it looks pretty similar from time group to time group. But if you look closely at the 0 to 2 second groups, specifically from the outside of the ice, like towards the boards, you're a lot more likely to shoot from kind of the corner area, and not quite the corner, but like right around the hash marks towards the net at that point than you are 11 plus seconds into the play. This is mainly due to the fact that, you know, like at that point early on in the play, if you take a shot, you're probably looking for a rebound from that angle. And there's going to be a much better chance that you're going to have a teammate going in and crashing the net for a rebound at that point than you will later on in the play when there's 2 or 3 defensemen right in front of the net.
And to just kind of build on that quickly, We can maybe talk a little bit more about this later, but you will notice that the structure of these maps in particular do look pretty similar, even if they're changing a little bit. And that's also partly by design. So in these models, we're actually able to sort of model the time dynamics as like an AR1 process, where we're estimating sort of how much information should be shared between the time steps. So in some of our models, we end up estimating that, you know, it changes quite a lot over time, whereas in some models, we end up estimating that they should share a lot of information over time. And that's really important, especially given our kind of like data limitations to be able to fit these sort of things. We need to be able to share information when it's reasonable to. So in different models, how much information is shared temporarily changes. Just to kind of back up a little bit and talk really kind of quickly about how do we get a model like this? How do we actually fit it? Like Brennan said, we end up using something called INLA, which stands for Integrated Nested Laplace Approximations. This is a fast way to do approximate Bayesian inference. There's a really nice package called RINLA, which I recommend everyone check out. And compared to a lot of other kind of Bayesian softwares out there, a lot of them work kind of on this probabilistic modeling level, where they try to give you as much flexibility as possible, and they do the sort of best they can to kind of fit those models, typically some sort of MCMC algorithm or something like this. INLA's philosophy is very different, where they say, okay, we're just going to focus on a relatively small class of models, but we're going to try to fit them as fast and as well as absolutely possible. And that class of models is called latent Gaussian models, and it really includes a lot of the very important models to statistics, like GLMs, generalized linear mixed models, generalized additive models, and even some of these kind of space-time models like the ones we're using here. The kind of details of INLA are way beyond the scope of this presentation, but the way this kind of works is because the kind of difficult part to approximate, like the things like the spatial effects with like different hyperparameters and stuff like that, is sort of specified to be normal or Gaussian. And it turns out that this allows them to sort of target the marginal posterior in very clever ways. There's things that they can kind of integrate out, and the terms that are left, they show that can be very well approximated using sort of different numerical methods like Laplace approximations and stuff. So given this kind of class of models, this is a really like nice, clean, and fast way of dealing with it. And I'm going to talk a little bit more about how we got those sort of nice pictures that Brendan was showing before. So Brendan mentioned this sort of mesh feature, and this is really common in almost all sports work, where you really want to think about the ice in some continuous way, but it's too computationally burdensome to actually treat the ice as continuous. So normally what people do is they find some way to chop the ice up, and they treat each kind of region of space in the way they chop it up as sort of homogeneous or as the same in those regions. Something very special we can do with INLA is we don't actually have to treat each region within the triangles as the same. So in fact, we can represent each point on the ice as a weighting of the 3 nearest points. So each kind of point on the ice is not actually just treated the same, but some weighting of the 3 nearest points. And each point or node is going to be a sort of a coefficient in our model. And this is really nice. So even though we end up estimating something that is discrete, the resulting maps can be continuous, which is why the estimated maps that we had didn't look like triangles. For example, you couldn't see that in the structure. A little bit about like mesh design. In general, what we want is smaller triangles wherever we expect really large changes to happen, and where we think that we can actually estimate that change. We have enough data for it. And this is not something that we really explored well enough, I would say. And it's kind of left for future work. There's a lot more that we could have done to sort of optimize the mesh, especially across different models. And like we're going to kind of show, we had, I think, close to 40 something models, and kind of in the time frame that we had for this project, it wasn't feasible to be able to check all of these things. But I think there's a lot more work that could be done to make these models better, exploring these kinds of things. Further, so we have a coefficient for sort of every node in the triangle here. But that's not really enough either. We kind of know from hockey or just from sports generally, we expect things close in space to behave reasonably similarly. So the way that we're going to impose that is using some sort of a Gaussian process. And specifically, we're going to use a maturing covariance function to sort of define what we mean by close. And things that are closer in both space and time are going to share more information. And so, yeah, we're basically using a certain type of Gaussian process. And there's a really nice kind of, for theory nerds, if there's any here, you can end up thinking about the models that we get as a unique projection from a continuous SPDD onto our discrete mesh. I forgot to update the actual reference. I have the, still have the 2012 with the question mark. There's a Roux et al. Paper that's really good that kind of shows this. Continuous SPDs or stochastic partial differential equations are used in, like, you know, physics to model like heat equations and stuff like this. And it turns out you can show that this is a unique kind of projection from that really nice theoretically continuous model onto something that's discrete, which is a nice thing to have. Now, in order to make a really complicated model like this work, we need to have reasonable priors, especially in the Bayesian context. There's two important hyperparameters in the maturing covariance function. We can think of them as the range, which is generally how far across the space or on the ice do we expect the correlation to fall below 0.1. And there's a spatial noise term. In these kinds of models, which are like non-regular, it's really important to have good priors, and those priors are going to impact things like the asymptotics and the rates that we're going to achieve those asymptotics. And we're going to use something called penalized complexity priors, which are really nice, and they're implemented directly in our inla. The way they kind of work conceptually is we think of a range of simple models to complex models. So the simple model is a nested sort of simple model. And in this particular case, that simple model would be infinite range and zero variance. So in other words, infinite range would mean we treat the space as the same everywhere. So everywhere on the ice has the same probability of whatever event we're talking about, and zero spatial noise. On the far end, we have zero range, as in each like inch we move on the ice, we expect radically different probabilities of different events to occur, and like sort of an infinite variance. And so we think of this sort of distance, and the prior we put is basically penalizing how far we are away from that simple model. It's a little bit more complicated than this, but it's sort of like putting a prior on Occam's razor, where we're going to favor simpler models without a lot of evidence to the contrary. So yeah, and we use the KL divergence, and there's kind of an information interpretation of how much information are we losing by using that base model. And so we can kind of put our hyper priors directly on these nice sort of tail probabilities. And these are easier to think about. And also, given our data limitations, it's nice to be able to, if we're going to use really complicated models, we use priors that sort of limit how much overfitting that we can do. So that's how we end up getting these models. We use this kind of mesh structure. You get these sort of individual maps, and we combine them, like Brendan said, to get probabilities. And the thing we don't really see in this diagram, again, is the sort of time component, but we're also thinking about a time component in these models.
And now moving on from the action models, we can start looking at how we get value out of our simulations. So for our simulations, we use expected goals as our measure of value. And for those of you who don't know, expected goals in hockey is basically just like a logistic model on shots to predict the probability that they're a goal. And in our model here on our first go, we kind of split things up into two different expected goals models. One with pre-shot movement, as you can see by the spatial maps here, and one without pre-shot movement, which we'll just pull up in a second here. But yeah, like basically we have the same sort of spatial maps, but now rather than the heat representing an effect on the count like it did in Poisson regression, since this model is logistic, the heat will represent kind of the effect on the probability that you score. And with both of these here, you'll notice they have a similar sort of pattern. And that's obviously when you're close to the net, you're more likely to score. And also as the play goes on, you're a bit less and less likely to score, kind of capturing that same rush play versus established offense idea that we had earlier. And with these models as well, we also ran into a few different issues with them. So we just wanted to quickly touch on those. So the first thing was the main reason why we split up shots without passes versus shots with passes before it was to try to incorporate a second spatial effect. And that spatial effect would take into account the coordinates about where the pass came from. And as you can see on the left, that map didn't end up working out that well. It ended up being very choppy and kind of nonsensical. It doesn't really have, there's not much intuition behind it there. And then also you'll notice if you take a closer look at the spatial covariates on the linear predictor scale as shown in the legend there, it's not really that close. Like it doesn't have a major effect relative to where the shots actually came from.
Yeah, so it was kind of, a bit of a disappointment. We thought it'd be really cool. We have these two spatial effects, this would be a really cool model. It didn't seem like we had the data to be able to sort of estimate the effect. And there's a little bit of complications in terms of we might expect different levels of smoothness for the two maps, and that can be sometimes hard to specify in INLA. But yeah, with more data, it's something we'd like to try again. And something we didn't really do in all of these models, but might be worth it, is kind of forcing a symmetrization. So one of the things that we noticed about this map is we just didn't have very good symmetry, which isn't really what we would probably expect. One way to sort of force that would be to just flip all of the coordinates onto one half of the ice and estimate the spatial models sort of on those flipped halves. That also might save us a lot of computation and just allow us to better estimate things more generally. That was something we kind of thought about, but didn't have time to explore, especially if we don't have the locations of the other players. It seems like something that would be worth trying. And the last kind of type of model, so those, we've talked a little bit about state and action, we've talked a little bit about our value models, and the last sort of set of models that we said we needed to be able to do our forward simulation is the sort of space, time, and context. So if you're going to do the kind of forward simulation that we did, if you kind of notice all of the kind of models that we've shown you up to this point, the main covariate we've been talking about has been the location, the X and Y location. And so having models which can predict the X and Y location of the sort of next event, especially in this discrete kind of setting where there might be many seconds, for example, that pass until the next event. And so there's obviously lots of possibilities of where the next event could occur. If all of our further predictions are going to be based on that X and Y, the X and Y models need to be very good. And this is something we found out the hard way. The first time we tried to do our simulations, we just had basically a placeholder model for the X and Y, which I assumed would be, good enough. But it turns out for a variety of reasons, we were really getting very rubbish sort of possessions. They weren't looking like our data at all, and they were very nonsensical. Things would get stuck in corners or in weird parts of the ice that it wouldn't make sense to have possessions. And so some of the reasons why it's difficult, well, you want the X and Y distribution to be updated jointly. That's a little bit difficult. And then also there's sort of like irregular dimensions of the rink. So if you especially think about the areas like behind the net, and there's also like things about like the space that the goalie occupies and the net itself kind of introduce these like irregularities in the sort of spatial features. And so those things were kind of difficult to accommodate. In the end, we found a model or a way of doing this, which we think mostly worked. So we fit the X location first, given the sort of previous event that happened, and you can see those models on the left. Some of them are quite nice, especially if you look at the recovery in the past, which are things we had lots of data about. Those are really nice looking maps. And then given the X location, we fit the Y location. That was one way of just kind of chopping up the joint density of the X and Y. And we use sort of a similar technique as we do for the having a spatial effect, where we have like a one-dimensional, essentially spatial effect on the X location, which gets fed into the Y location model. And And then again, kind of going back to the fact that we're fitting all these models in INLA, and the kind of first thing we talked about with INLA is that INLA restricts the kinds of models you can have, which can be difficult when you have lots of constraints. Like in this case, we have constraints coming in essentially 4 dimensions. And the only likelihood that it performed any reasonably on this data was the beta, because it lives in the open interval 0, 1. So we were able to map the offensive zone into a sort of open interval box on 0, 1, 0, 1, and use the beta likelihood, and that worked quite well. It turns out also the sort of mean variance relationship of the beta matched the kinds of patterns we were seeing in the data as well. And yeah, the difference between using that model and not that model was extremely large. And especially if you want to do this approach with kind of simulation, these models end up being super crucial. And so that's something I guess anybody that's going to try this kind of thing would need to know.
Yeah, and sticking on the topic of the space-time and context models, we just wanted to narrow in on the context models and describe how we use those really quick. So looking at the passes in particular, or sorry, the shots in particular, one thing we had in the staff weeks data that generally wasn't available in the public was additional variables about like whether there's traffic or not, whether there's a one-timer, and whether there's a deflection. And we wanted to include these in our expected goals model. However, the issue with that is that we have to simulate the one-timer, the traffic, and the deflection at some point. And in order to do this, we built out kind of a sequence of logistic models, as you can see here in the model column of this little table here, where basically we just simulated from these models one by one, where we kind of add in basic covariates for all of them, such as time since last shot or time since last pass, was the shot from behind the net, and that spatio-temporal effect that we were talking about earlier. But then we also, as we go and we run these models and get simulations from them, so we run the one-timer model and we get a value or like a yes or no value from that, we can add that as a covariate into the traffic model. And then once we run the traffic model or get a simulation from the traffic model, we can add both that and the one-timer into the block shot model and keep repeating this process over and over, adding new covariates as we go. However, there's a bit of a hitch with the block shot and the miss shot models. And that is that we can't really add these as covariates into other models because really they're just outcomes of what's actually going to happen with the shot. So for example, if the shot misses the net, then we can't really use that as a covariate in the goal model. We just assume that if it does miss the net, then there's no chance you're going to score. Right, so that's kind of how we do that. And that allows us to incorporate these new covariates into our expected goals model in our simulation chain.
And the kind of a second side benefit of that is we would expect the next like spatial location of a block shot and a miss shot to look quite different than a shot on net. So that allowed us to get better sort of downstream models and kind of splitting those sort of outcomes. It took a lot more work, obviously, but splitting those things allowed us to get sort of better, more realistic simulations. So putting that all together, we've talked about these 3 types of models. We have these value models, we have these state and action models, we have space-time and all these contextual models. So now we need to jam them all together to get something interesting. So kind of bringing us back to the beginning, if we suppose we start at that green dot, what we're going to do is we're going to chain all of these models together. We're going to run a number of simulations until those possessions, each of those possessions end. In gray, you can see a bunch of different simulation paths, all starting from that same point. And following our rules about how expected goals are accumulated, each of those paths will have some number of expected goals. And we can actually just look at that distribution. And so on the right, you see the distribution of expected goals produced from this particular point in time. You see most of the simulations end in 0 expected goals, as in there's no shots that occur. But there's sort of a large tail all the way up there. There looks like there's a couple possessions out of the several hundred, which ended with several shots that were high quality with like 0.2, 0.3 sort of expected goal value. So that's how we're going to end up valuing different locations on the ice, and we can do similar thing for valuing like particular actions.
And yeah, like Tyrel was mentioning, now we can use this expected possession value to get the value of an action on the ice. So for example, if you take that blue point there right in the middle of the ice, and we observe a shot from that point, and we want to get the value of what that's actually worth. So in order to do that, we need three things. So we need the expected possession value at the moment prior to taking the shot. We need the expected goals from taking the shot, and we need the expected possession value at the next observed moment after taking the shot. And once we have these three things, we can plug them into what we call our possession added value formula. And this is basically kind of like the value that you add to the possession by taking that action. And we use this formula as follows, where we add the expected goals, or like the probability you score, plus the expected possession value at the observed moment after taking the shot, multiplied by 1 minus the expected goals. And we multiply this by 1 minus the expected goals to take into account the possibility that you actually do score on the shot. So for example, in this case here, there's a 7.8% chance that we score. And that means that there's a 7.8% chance that we don't even observe the rebound there, or that next observed moment. So we have to downweight to account for that. Then using these two, these first two components, which are kind of like the value you have after the shot, we're going to subtract off the value that you had before the shot. And that gives us sort of an opportunity cost of taking that shot. And in the top right there, you can see we have a nice distribution there. So like Tyrel was mentioning, with the expected possession value, we get these distributions of value. And we can use these to turn that into another distribution of value for this single action. And one other thing, just when we're not looking at shots, so for any other action, rather than having this formula here, we're just going to simplify it by setting expected goals equals 0, because we assume that we can't score off of a pass or a recovery or anything else. And that's just going to simplify the equation in that we just get rid of that first term since it's zeroed out. And the 1 minus expected goals multiplier there just becomes 1. So that kind of disappears as well. Then you're left with the expected possession value at the following moment we observe minus the expected possession value at the moment prior to taking the action.
So that's how we value different sort of actions with these kinds of models. And then we can sort of accumulate, like we said, we want to value players in some ways. So one kind of naive way of looking at players is we look at all the actions that they take, and we sort of accumulate the expected values or the added values from taking those actions. And like, again, because we're working with distributions, we end up getting distributions. So on the left here, we have the sort of distribution of total added value for a particular Erie Otters player, who I think, according to our model, had the most added value, Chad Yetman. And on the right, there's sort of 12 players where you can kind of see a credible interval of like how much added value we think they contributed based on the actions that they took. And these are really nice, I think, demonstrations of what's possible with this kind of model. But remember, a lot of the work that we did was to kind of deal with the fact that we didn't know where the other players are on the ice that aren't taking the action. So we do have to be very careful when we're interpreting these downstream metrics, and we expect there to be some kind of confounding with where the teammates and the defenders are, which is going to be impacting the kinds of actions that the players are going to take, and is going to be related to sort of the value. So we partially capture this by dealing with the time since entry thing and sort of integrating over the uncertainty, but we're likely to be fooled if we take this too seriously. But we think in kind of future iterations of the model with like a slightly different data set, we would be able to account for at least some of these issues. A good particular example where we really ran into this head on was passes. So if you look at these graphs on the right, you see the majority of passes happen like along the boards. And in general, the areas around the boards are not particularly valuable. And depending on how you kind of account for this, we found that most passes had almost no, or maybe even slightly negative, or just barely positive sort of added value. And a lot of players had like overall negative value from passing. But these are really highly skilled players that are trained to make good decisions. So it's quite likely that when we observe them making a really low value pass, especially with like the kind of frequency that we did, it's likely that there's a reason that they're doing that. Like, for example, maybe they didn't have other good options or they were about to lose the puck. And in those cases, it's much more likely, it's likely that the pass was actually valuable and that it mitigated some other sort of action that was low value. Some of this could be taken into account by modeling both sides of the possession. Like, these things are likely very low risk in terms of turning into value for the other team. And so possibly that's part of the issue here as well. But in any way, general caution about sort of interpreting these kinds of things. But we do think that we could account for at least some of them in with better data. So where does this kind of go next? Naturally, we're going to just talk really briefly about this. I think we're running out of time, but we wanted to be able to do this at the full ice. There's a couple complications, like when do possessions end on the full ice? It can't really be when just the puck goes out of the zone, for example, or if it does, and that way we have to be careful about what we mean. Hockey has this really like interesting structure with all of the sort of offsides and the way play is quite different between the offensive zone, neutral zone, and defensive zone. And we're going to need to be able to model, how it flows between those zones and the sort of actions that are available in those zones. We can't just do expected goals for. We need a joint distribution over the expected goals for and against. And an additional kind of complication with our branching state where we want to think about the value after a goal and no goal. Now, when you get a goal, we know that there's going to be an outcome, which is a face-off at the center ice, and we want to account for the sort of value that we expect both teams from that point in space and time going forward in the rest of the game. That's not difficult from a practical standpoint, but it took us a while to realize that that was something we would need to add. And there's obviously just a lot of computational difficulties. But I'm going to give, I think we solved at least some of the important problems, even though we haven't quite done this. I'm just going to let Brendan really quickly give you a flavor of what that might look like.
Yeah, for sure. So like Tyrel was mentioning, this is kind of a bit of a visual intuition about what the full ice model looks like. So if you remember that Markov process that we had for action transitions, this is very similar, or this is the same idea here, except now we're looking at the full ice and we break things up into different zones. And we do that for the purpose of the fact that like a pass in the defensive zone might lead to different follow-up actions than a pass in the offensive zone. And another cool thing about this is, like Tyrel was mentioning, we kind of had a bit of an issue where does the play end now? And here, this chain here kind of fully simulates through where we go from face-off to whistle, and we can just cycle through that if we'd like. So now we can pick up from any play or any play on the ice and kind of simulate forward from there.
Yeah, and like Brendan's saying, like there's probably there might be a more clever way to end possessions earlier. But certainly the safest, at least from kind of thinking about it like a decoupling, seemed to be whistle to whistles. Like once you enter kind of a whistle state, there's certainly kind of a clean break, and the only thing that should matter is like the state of the game at that point. Maybe there's ways to end the possession earlier, but we weren't clever enough to think of that. So this seems safe and at least a reasonable first step.
Yeah, and moving on from there, like in terms of how we actually simulate things, this kind of gives a bit of a simplified version of what our simulation chain would look like. So it's a while loop where we keep going until we observe a whistle. So for example, here, if you see a shot at point XY, then we're going to predict the contextual information using those shot context models I talked about earlier. Then once we have that, we're going to predict if there's a whistle or not. And if there is a whistle, we stop. If not, we keep going, and we predict which zone the next event will be in. And then given that, we predict the XY coordinates and time elapsed until the next event. And then finally, given all that knowledge, we predict which action will occur next. And we just keep cycling through this loop. And if we ever run into a turnover, then we basically just flip the coordinates around and simulate forward from the other team's perspective.
Great. So yeah, so that's pretty much it. And where we want to kind of go with this, we want to finish this full ice model There's a lot of work that could be done on like optimizing and validating the particular submodels. We were using things like, WAIC and stuff like that to compare some of those submodels, but certainly didn't explore the full extent of it. And like we talked about the mesh design and these kinds of things. We think we could extend this pretty reasonably to have the location of all of the players on the ice, even though it might increase the computational load. But we think there's the structure there to be able to do it. And that would help us, work with kind of more interesting data sets. We also think this would open the door for a lot of interesting stuff about simulating like particular formations or looking at different kinds of particular contexts of like 2-on-1s and these kinds of things. So what do we expect happening in those contexts? That's where, working with people like Mick and Thibaut would be really useful to kind of figure out what's useful for coaches. We also think this would solve some of our selection bias issue. And maybe allow us to evaluate decision making. We would have all of the options available to each player, and we could kind of think about how optimally did players act. But we do need to think really carefully about how we're going to attribute value to players, because it's likely that some of the value that gets attributed to actions are actually due to other players that are not necessarily touching the puck. So there are some additional problems there, and maybe we have to move to the kind of model where we condition directly on player effects directly to take that into account. It's not entirely clear. But that's basically it. Here are a few references, and specifically if you're interested in like work that we sort of did on the more applied side of things, specifically Mick and Thibaut's work, there's a nice Hockey Graphs article, the second one, where they sort of use these models and the outputs in the context of a sort of traditional scouting. How can you augment sort of a traditional scouting exercise for teams or players with these kinds of models? And I think that was really well done. And yeah, if you're interested in the more applied side, especially, that would be a good place to look.
Excellent. Well, thank you very much for that talk, and very methodologically comprehensive. So I'm looking forward to audience members asking some questions. Please just feel free to unmute yourself and ask away, or if you want, you can put in the chat as well. It's up to you. So I'll just ask a couple of like very superficial questions while we're waiting, but like how long have you guys been working on this? And it seems like this would have had to have been a very long time in production.
It was not. So I guess it's hard to remember the timeline because things are very blurry, but I think it couldn't have been more than 6 weeks in the original submission because of the Dateable constraints. And then we definitely worked on it a lot between the submission and the kind of when the final presentation was. There was about an extra month. And then I think we had a lot of time for maybe another month or so after that, but then both of us and plus our other partners on this got very busy with other stuff. So I don't think we spent more than maybe 3 months, but it was an extremely intense 3 months. And we definitely got lucky that we were able to finish as much of it as we did in that time. We were being way too ambitious probably for our own good, but it happened to work out.
Yeah, that process, like the competition kind of must have drove something out of us, because I remember being up until like 2 or 3 in the morning a few nights trying to get the simulations to work, but we just get it in the last couple of days there.
Yeah, definitely Brendan must not be able to operate on very little sleep, because yeah, like of all the models that we had, pretty much every one of them was trained on his MacBook, which yeah, a lot of work probably went into that.
Yeah, it was nice though. I didn't have to deal with much of the theory. Tyrel kind of, every time I asked Tyrel a question, he would say, "Let me think of that," and then come back about 10 minutes later with like a 30 message thread on Twitter for me.
Okay. Excellent. Yeah. So Tom, I think you had a question there. Sorry, I interrupted you.
Yeah, no problem. Thanks very much for the talk. I I just love these kinds of talks. I did have a question about your triangle mesh. It looked like your triangle mesh filled a rectangle rather than the sort of D shape of the offensive zone. And you had a lot of triangles, particularly the fine mesh seemed to be out in space where the puck doesn't go.
Yeah.
And I was just wondering if you could comment on that. Does that have an effect on your ability to model what goes on in the corners?
Sure. Yeah. So yes and no. So in general, for these types of models, it's basically really harsh to have sharp boundaries. So you always kind of have like an additional kind of some kind of filler around the area of interest. Yeah, just to kind of keep the kind of continuity. And for a lot of the models, that's not a problem. Like for example, in these models we see there with the actions, like the entire probability space is contained exactly within the rink, even though technically if we wanted, we could make predictions slightly outside of that region, but they would be nonsense. But for the location model specifically, when we get to the location models, we didn't map, because of the way the likelihood works, we mapped everything to the 0-1 box, but without changing the kind of curved areas. So in those cases, that did have an effect on our simulations. And if you look at, I think, the very first slide, you'll see that there's a couple here. There's 2 or 3 on the kind of upper right corner. You'll see 3 points that are just outside. So in general, even though we had that issue, very few simulations ended up going there because the models were, strong enough to kind of stay away from that. But the location models technically did have the issue you talked about. We could fix that. That is something that is fixable by just sort of changing what 0-1 means behind the net. But we didn't have time to quite integrate that into the model.
What, like making 0-1 fractional relative to the distance between the blue line and the end board?
Yeah, like just kind of, like the end board.
0 to 1 is the distance between the blue line and the goal line when you're right along the boards, and then 0 to 1 is the goal line is actually at 0.9 or something when you're in the middle of the. Yeah. Okay.
So we could do something like that, and maybe there's something even more clever that we could do with that. I'm not entirely sure, but that was kind of our first thought. But yeah, the location models did have that problem, but everything else doesn't really suffer from that.
Yeah, okay, because I was just worried about it because you talked specifically about putting the finer triangle mesh along the boards where a lot of little ticky-tack stuff happens, but then here that is sitting way out there in nowhere space, and you have a broader triangle mesh right in along the corners where a lot of ticky-tack stuff happens.
Yeah, it probably should, like a better mesh for these things, like you said, it should be like a bigger kind of thing on that outside. It shouldn't be so tight. But yeah, for most of the models, it didn't seem to impact.
No, it didn't seem to, and I was definitely happy to see that, but I just didn't know if it was something that you thought about or was fixable. Okay, thank you.
Yeah.
Right on, thanks, Tom. Who wants to go next?
I do. This is Jim. I just wanted to ask, did you have a learned model of where the shot would go on the next stage? I might have missed that in the presentation there.
Brendan, do you want to take this?
Yeah, so like the location and where it would go next?
Yeah.
Yeah, so we kind of did that in the location models. I think Tyrel's gonna pull it up here.
Here it is.
Yeah, so our location model is kind of, rather than splitting the plots up by time like we did with some of the other ones we showed, this one split it up by event. So as you can see here, you can kind of see the shot one there on the kind of like in the upper right one for the X and the Y. So then as you notice there too, it kind of does look a bit different, which it should, because shots are directed at the net, so it's going to bounce. Weirder things are going to happen than when you're passing, right? Where you're generally just passing like in a straight line. Generally there's a lot of D to D passes or like kind of around the perimeter passes, so they're going to be a bit more well behaved. then yeah, you'll kind of notice on the Y one there too. If you shoot, say you shoot from around the right circle, then you're more likely to end up kind of more towards the board than if you shoot, or yeah, you're gonna more likely end up kind of towards the left side of the ice. Whereas if you shoot from the left side of the ice, you're gonna kind of end up by the right side of the ice.
Right.
Whereas if
Right.
you look at a recovery, it kind of sticks around the same side.
And this represents some sort of distillation of the information you got from the sequences of events. Is that right?
Yeah, so yeah, it's basically, it's just built off of the data. So we just look at what event comes next and where it goes.
Right.
Then we kind of use that to predict it.
Right. Right. Somehow inside there's some information buried about where the other players are too.
Not the other players. So we just really have the player who takes the shot, or like the players that are involved in the event. So that was kind of a bit of a problem with our data, was that we only have kind of the
Yeah.
events and where it is and who's involved, but we don't have anything else. So that's something that can be cool to add in.
It would be cool. Yeah. Thank
Yeah.
you. Nice presentation.
Thanks.
Thanks.
I imagine that some of that information is is very implicit in the
Yes.
results. You have a guy standing in front
I
of the
agree.
net and he's not taking a
Mhm.
shot. Why is that? It's
Yeah.
because there's somebody in the way.
No, totally.
Yeah,
And-
exactly.
And I think you addressed that, Tyrel, when you talked about how these things can't be taken as causal.
Yeah.
Yeah.
Yeah, that's exactly right.
You shouldn't expect always to have the same expectation every time a puck goes to a certain spot. It's very situation dependent.
Yeah.
So then the next step has to be to figure out what the situations are. But you have to start with this. This is interesting. You know, they learned a lot in basketball when they first started mapping out what the expected values of shots were taken from different locations.
Yeah.
So
No.
so complex work like this is really good.
Thanks, Tom. And Jim, next question. So Brendan, so it sounds like you're the computation person here, if I've got that right. So how long does it take you to, fully simulate, and are you limited in the number of runs you can do, and would it help? Like, are you achieving convergence, I guess, in your estimates?
Yeah, actually, that's another thing that we didn't really touch on. We didn't really have time to touch on, was the simulation process that we undertook. So it did take quite a while to simulate all these plays. I can't remember the exact time, but I think it was like 1 simulation per second, which kind of sounds pretty quick, but when you're trying to do a lot of simulations on a lot of data, that really quickly gets overwhelming. So what we did is we did like as many simulations as we could. Then we fit a model over top of that, like a zero inflated gamma model, if I remember correctly, to get the value, or like to get the expected possession value of each play, like to get a distribution for the expected possession value of each play, rather than just doing it based off of simulations, which would have taken a lot longer. So yeah, that was kind of Tyrel's idea there again. If you had anything to add to that, but
Yeah.
Yeah,
We kind of, especially early on, before the initial submission, like you said, yeah, these simulations were taking too long for like one laptop. It's the kind of thing with like, lots of, a big supercomputer and a bunch of cores and stuff like that would be less of an issue. But we did also want to kind of think about having some flexibility, especially if you were thinking about this from the context of a team or something like that. You wouldn't necessarily want to have to, after every game, in order to get the value of every play that happens, which could be, thousands of new things, you wouldn't want to have to therefore run like 1 million simulations or something like that to get the values of those things. So we wanted to kind of pair that, and yeah, we didn't get to talk about this here, with sort of another sort of approximation method. And so you get these kind of, what you can do is, I guess you can basically grid up or take a nice random sample over the ice, and you take enough simulations from every major action point, from every kind of major point, you get one big group of simulations. You can do that once, and then you can kind of train a model to that information, which should give you a little bit more information than the initial, like the raw data, just because you're not going to see all of those different types of sequences, at least in the distribution that you want, because they're very spatially clustered and stuff like that. So that was one thing that we kind of looked at, and probably where this work would go forward, or how you would use it with a team, would be you would want a mix of both. Like, I think the simulations are better, and like we said, especially with conditioning on the different players and stuff like that, I think there's a lot of really interesting things that you could do with the simulations that you wouldn't be able to do otherwise. But also, again, if your goal is to just sort of get the expectations, which most of the time that is probably what you want anyway, you can kind of do these kind of further approximation methods at the end.
Right on. Thanks for that. Okay, any parting questions? Okay, so I am going to stop the recording here shortly, but I just wanted to thank you both for a really, very profound talk, and excellent job. And yeah, thanks again.
I appreciate it. Thanks for having us.
Yeah, thanks for having us. It was great.